Hello everyone. In this lecture, we will see Boolean algebra. This algebra was given by George Boole, and this Boolean algebra is nothing but a set of rules that is used to simplify the logical expression. If you have a larger logical expression, by using this Boolean algebra or the theorems or rules, we can simplify the logical expression but without changing its functionality. That is actually important point. That means we cannot change the functionality, but anyhow we are minimizing the expression by using some set of rules. So let's see these rules, and then we will see how we can implement in some Boolean function, and we will try to minimize that expression. So let's start with the rules. So first rule, so here I'm starting with the rules, and inside that first rule is a complement rule. This complement rule says that 0 complement will be equals to 1, 1 complement will be 0. Similarly, complement will be represented by a bar. If the input is a, then a bar will be the complement. If you are having the double complement, then you will get the same expression as a. So these are the three equations which are very important. The representation of a complement of input, if input is a, will be a bar. The complement of 0 will be 1. Complement of 1 will be 0. If you take a double complement of any input, then you will get the same input. That means double bar of a will be equals to a only. That is the first rule inside the Boolean algebra. Let's see the second rule. That is the AND operator rule. AND operator rule. This AND operator rule says that a dot a, that means a logical multiplication, will be a. With that we can prove also. If you have a single input a, that means 0 0 0 1, because there is only two possibilities. And again, if I write a only, that is 0 1, and I will take the logical multiplication between them, then I will get 0 1 only. That means if you are taking the AND operation between a and a, then you will get the same expression as of a. That means a dot a is equals to a only. If I take a dot 0, if I perform a logical with means multiplication with 0, will get 0 only, because as you know that multiplication with 0 will give you 0. Any number if you multiply with 0 will give you 0. That's true. If I multiply a with 1, let's see what will happen. If this is a, that means it can be either 0 1, and I am multiplying with 1. 0 multiply with 1, you will get 0. 1 multiply with 1, you will get 1. That means you will get the y is equals to a only, right? The same expression I am getting, whatever as will be the input, same I am getting as the output. That means a dot 1 will be is equals to a only. Now the last one, that is a dot a bar will be what? That we have to calculate. So let's see. If I am taking a here, that is 0 1, it can be either 0 1. I will take the complement of it, that means 1 and 0. Then if you take the AND operation between them, I will get 0 multiply with 1 will be 0, 1 multiply with 0 will be 0. That means if you take a dot product between a and complement of a, you will get 0. So these are the four equations that come under the AND operator rule. Now we will see the third rule inside the Boolean algebra. That is the OR operator rule. So this is the OR operator rule. If in the OR operator, if I take a plus a, what will happen? So if I am taking a here, that is 0 1. If I take another a, that is also 0 1. If you perform the OR operation between these two, you will get 0 1. That means the same you are getting, right? So if you perform the OR operation or logical sum operation, then you will get a plus a is equals to a. If a plus 0, what you will get? So if you perform A, this is 0, 1, and you are adding with 0, 0. So you will get 0, 1 only. That means again you are getting A. So if you are confused with some equation, you can solve. That will be the better way to remember these equations. Okay, so for example, I want to do A plus 1. What I will get? A, this is 0, 1. This is 1, 1. If I will take 1 plus A, or A plus 1, I will get 1 bar. That means A1 plus A is equals to 1. The last one is what? A plus A bar, and we have to check what output I will get. So if it is A plus A bar, that means this is A0, 1. A bar will be 1, 0. If you perform the OR operation, that is A plus A bar, I will get 1, 1. That means also A plus A bar will give you 1. So we have seen OR operator rule also. Inside the Boolean algebra, the fourth part will be the distributive law. That is very important. Distributive. This distributive law says that A dot B plus C, if you distribute it, if you open it, then you will get A dot B plus AC. Similarly, if I am writing A plus BC, then first you take a OR operation with B, that means A plus B, and then you perform A plus C, right? So this is A plus C. And this is actually the important, because most of the time we get this type of equations where we need to provide the distributive property or distributive law. Now, inside the Boolean algebra, the fifth rule or theorem is the commutative law. This commutative law says that A plus B is equivalent to B plus A. Similarly, A dot B is equals to B dot A. So either you take A plus B or B plus A, both are the same thing. After this, we have the sixth rule in the this Boolean algebra, that is associative. Associative law. This law says that A dot B in bracket C is equals to A dot B dot C, like this. That means either you perform AND operation between A and B first and later with C, or you can perform the AND operation between B and C and later you can perform the AND operation with A. Seventh rule says that always give priority first to the NOT gate, then you give the priority to the AND gate, and then you give the priority to the OR gate. Then you give the priority to the OR gate. Next property that's come under the Boolean algebra is the De Morgan's law, and that is actually the important point. De Morgan's. De Morgan's law is A plus B whole bar is equivalent to A bar dot B bar. Similarly, if it is A dot B whole bar, then you can write on A bar plus B bar. Let's see some questions how we can apply. So these are the 8 rules, and we should remember these rules for simplifying the expression by using the theorems. Let's see some numerical equations, and we will try to minimize these equations. So let's see if first question I am taking. That first question, y is equals to for example, we have the equations like this. AB bar plus ABC plus AC bar D. So how to start this question? Y is equals to, as you can say, A is common term. So we will take A common. Inside this you see, this is B bar. plus BC plus C bar D. Right? What I did, just I have taken this A common. Now, after this, in this term, can we apply the distributive property as we have seen earlier? So that we can write on B bar plus B, and this is B bar plus C bar D. And we know that this B bar plus B is equals to 1. So I can write down as A B bar plus C bar D. Correct? Now you see, with these two terms, can we apply a distributive property again? Yes, we can apply. And we can write down like A, this is B bar plus, this is what? A C plus C bar plus, and this C plus D. And as we know that C bar is equals to 1, so we can write down A, this is B bar plus C plus D. This is the answer for this question. Let's see one more question related to it. So if it is like, the question is, second question I'm taking, y is okay, f is equals to x y z plus x bar y plus x y z bar. For example, this is the question. So how to start this type of this question? Try to take the common terms, like in these first and the last. We can take xy common, that is z plus z bar plus x bar y. Z plus z bar is equals to 1. So you can write down xy plus x bar y. Now you take y common, and that will be x plus x bar. That is equals to what? This x plus x bar is equals to 1. So the final answer will be y. Correct? Now we will see another question related to it. For example, we have a question like third question I'm taking. Y is equals to AB plus A bar C plus BC. Now here, just by seeing this equation, it's not easy to recognize whether how we can minimize or whether it's a minimized expression. So one theorem is there that is called as the redundancy theorem. So let's see what is the meaning of redundancy and how we can minimize this expression, which is not looking whether it's a minimized or not. It's a non-minimized expression. So let's see how we can apply the redundancy theorem. Redundancy theorem is applicable only if these three conditions are satisfied. The first condition is says that it should have three variables. If any expression is having three variables, second, each variable is repeated twice. And third, one variable is complemented. Then we can apply the redundancy theorem. So let's see in whether in this expression these three conditions are satisfied or not. So first thing is what? It should have three variables. Of course, we have A, B, C variable, right? So in this expression, I have A, B, C expression. Okay. Each variable is repeated twice, as A is coming two times, B is coming two times, and C is also coming two times. That means each variable is repeated two times. One variable is complemented. So A is complemented, right? That means we can apply the redundancy theorem here. So let's see how we can apply the redundancy theorem. So first I am writing the expression, and then I will tell you how we can apply it. So y is equals to AB plus A bar C plus BC. So how to implement? Here you see, here we have A, here we have A bar. So in the third expression, you have to include A plus A bar, because the total meaning is what? A plus A bar is equals to 1. So it will not change the functionality. So what you have to do, if you have one normal form, complemented form, then you have to include a plus a bar right here like this. So what you will get, just open this expression. This is ab plus a bar c plus this is a b c plus this is a bar b c. Now if you see, if I take these two terms and these two terms, so what terms we can take common, you see? If I take these two terms, then I will take AB common, and that is 1 plus C. Similarly, from second and fourth, I can take A bar C common, and that is 1 plus B. So as you know, 1 plus C and 1 plus B is equals to 1. So ultimately, the answer will be equals to AB plus A bar C. That means we minimize the expression, right, by using the redundancy theorem. So now we will see another question related to it. If you have any function f is equals to ab plus bc bar plus ac, can be minimized by using the normal theorems? No. Here we have to provide the redundancy theorem because it follows these three conditions. First one is what? Three variables should be there. A, B, C, three variables are there, satisfied. First rule is satisfied. Second rule says that each variable is repeated twice. Yes, here A is repeated twice, B is repeated twice, and C is also repeated twice. Third condition says that one variable is complemented. So here C is complemented. If C is complemented here, that means AB here BC bar plus AC. As C is complemented, you need to include C plus C bar in the third equation, third term actually. So now we can write down as ABC plus ABC bar plus BC bar plus AC. Now, if you see this expression and combine these last and first and last and second and third, then you can see if you take AC common, it become 1 plus one. So if you take AC common, it will be 1 plus B. Similarly, from the third and second, if you take BC bar common, so this is BC bar common, then it is 1 plus A. And you will get the output as AC plus BC bar because 1 plus B and 1 plus A is equals to the 1. Now we will see the third equation. If you have third equation F is equals to AB bar plus BC plus AC. For example, you have this equation and you need to minimize this expression by using the Boolean theorems or Boolean algebra. So by using the normal theorems is not easy. So we will go with a redundancy theorem. We will check whether these three conditions are applied or not. So we have checked that three variables are there, A, B, C. Then we have seen each variable is repeated twice, of course. Now we have seen one variable is complemented, B is complemented. If B is complemented, that means A, B bar plus B, C plus AC. With the AC, you have to include B plus B bar because this is already a complemented. So on the third term, you need to include the B plus B bar. Now you open it. This is A bar B A B bar plus this is BC. This is A B C plus A B bar C. Now, from the first and last and between 3 and 4, you can take the common term. So this is A B bar and you are taking 1 plus C common. From the from the second, third, you can take BC common and that will be 1 plus A. And that means you are getting the output as AB bar plus BC. Okay, now we will see the another question and which is again an important type of questions where we have expression like this. F is equals to A plus B, A bar plus C, B plus C. Again here by using the normal theorems, it's not easy to minimize the expression. So we will use the redundancy theorem, which says that that means each variables there should be a three variables, and each variable should repeat twice, and one variable is complemented. So here you can see a is complemented, right? So on the third term, we need to include the expression. So it is a plus b, this is a bar plus c. On the third term, as this is a POS expression, you need to include a dot a bar plus b plus c. Okay, as the expression is in the POS, we have to include a bar. If it is a SOP, then you have to include a plus a bar, like that. So now here, this is a plus b, this is a bar plus c, this is a plus b plus c, a bar plus b plus c. How we got this term? By using the distributive property. Now, between these two and between these two, you can take the common terms like this, right? So between these two, if you see a plus b plus 0 dot c, right? This is the again distributive property. Between 2 and 4 also we can take the common terms. This is a bar plus c plus 0 dot b. So ultimately 0 dot c or 0 dot b will be 0, and you will get what? A plus b, and this is a bar plus c. This is the minimized expression after applying the redundancy theorem. Let's see the another type of questions. So here we have one extra question. This is f is equals to wyz, for example, plus xy plus xz bar plus yz. So how we can do that? You see, from the first and last, you can take yz common. So I am taking yz common. This will become 1 plus w plus xy plus xz bar. So this will become yz plus xy plus xz bar. Now you see, from here, by using the normal theorems, it's not easy to minimize the expression. So what we will do, we will apply the redundancy theorem, and let's see whether these three conditions are satisfied or not. So here, if you can see, there are three variables. Yes, x, y, z are three variables. Each variables are repeated twice. Yes, y is coming two times, z is coming two times, and x is also coming two times. And one variable is complemented, z is complemented. So if z is complemented, so z bar is here, z is here. So between here in xy, we need to include the z plus z bar. So yz plus xy, here I should include z plus z bar plus xz bar. So this is yz plus xyz plus xyz bar plus xz bar. Now, if you take a common, so here if you take common between these two and these two, that's also okay. So now if you take yz common, so this is yz 1 plus x. And if you take from here, this is x z bar, so it is 1 plus y. So the final answer that you will get will be yz plus xz bar. Correct? So we have solved some questions based on the Boolean algebra, and we have also seen how to apply the redundancy theorem, because it's actually the important type of questions.